So let's chit chat about that assignment from yesterday, because this whole concept of spontaneity, if reactions are going to take place, is going to play out today on the discussion with what's called Gibbs free energy. So when you look at these E naught values, okay, so for example, you have Ag plus 1 electron turning into elemental silver at that 0.80 volts. Now, so on 35A, to balance that out, because you have copper at 2 plus and you have silver at 1 plus, you need to multiply all of these by 2. Now, here's what you're going to see different from thermodynamic calculations, which is what we're going to get into next, is that just because I multiply these coefficients by 2 doesn't mean that I multiply that voltage by 2, okay? Now, because this is what's called an intrinsic value, that 0.80 volts is going to happen no matter what. So when you look at what's a factor and what's not a factor, one of the things that's not a factor is like the size of the electrode. Whether I have a thin piece of copper or if I've got an ingot of copper, it doesn't make any difference, okay? So the size of the copper doesn't matter. It's not part of the equation. I can't plug that in if I have to. The only time...
Sorry. I'm listening, I swear.
The only time that you ever do anything with this value is when you switch it, okay? Because keep in mind, these are all reduction potentials, okay? These are reduction potentials. So if you switch this and turn it into Ag turning into Ag plus 1 electron, then you switch the sign of that. But by multiplying it by 2, all those coefficients by 2, you don't change anything. It doesn't change that positive 0.80 volts. If I double the size of the electrode, doesn't change anything, okay? So the only way you can change that 0.80 volt is if you switch the sign, because it changes from a reduction reaction into a oxidation reaction. So what you should see on 35 and 36, each of those is going to have one spontaneous reaction and one non-spontaneous reaction, okay? So that's what you should see on 35 and 36. So on 36, if you balance those, because those are much more complex, the 36 ones are more complex. So if all goes well, when you balance those reactions, you should end up with 16 hydronium ions, okay? So on 36, if those are balanced right, you should end up with 16 hydronium ions. When you get to question 47, you got to be wary of the wording on 47, because place the following in order of increasing strength as oxidizing agents, okay? So you want, the first thing you got to figure out is if you're looking at something being a good oxidizing agent, what are you trying to find? An ion or atom that's trying to lose an electron, or an atom or ion that's trying to gain an electron? Vanessa.
What was the question?
Okay. You're trying to find a good oxidizing agent.
Okay.
Okay, that's what you're after. Is a good oxidizing agent. True? Good with that.
Okay.
So, on a good oxidizing agent, are you trying to find an atom or ion that's trying to gain electrons or lose electrons? Why?
Because it's supposed to do with use.
Yeah. So, you're trying to find amongst this list, when you get down to the end, you should, at the end list, okay, of this list, when you get done at the end of that list, you should have the ion or molecule or whatever it is that's most willing to take in an electron. Now, this is the thought process that you need to go through. Oh, okay, right. I'm looking for an oxidizing agent. I'm looking for something that wants to be reduced, which means exactly what Vanessa said. I'm looking for something that's going to take in an electron. So let me say I gave you a choice. I said, okay, which would be the better oxidizing agent? Ag plus or Ag? Let's say we narrow it down to this. Which one would be the better oxidizing agent? Silver ions or elemental silver, or it's the same because it's silver either way? Evan,
The ion,
why?
because then silver will have a neutral charge, which it's fine with. But if you were to give the silver, elemental silver, an electron, that would be Ag minus, and metals don't like to be minus.
Fantastic. Excellent explanation. Okay? So silver itself as an oxidizing agent would be horrible. Okay? Because you're not going to take a silver atom, make it gain an electron, and turn into Ag1 minus. Okay? So if you look at your esteemed chemistry careers, have you ever seen Ag1 minus? No. Doesn't exist. Okay? It's like, oh, have you ever seen a cool freshman? No, they don't exist. The same thing is true of Ag1 minus. Okay? And you all weren't cool as freshmen. You all thought you might be. You weren't. Okay? No, Bergkamp, we were cool. No, you weren't. Okay? No, you weren't. Now, is Ag plus a good is Ag plus a good oxidizing agent? Yes, why?
Because it wants that electron.
How do you know? How could you look at a chart and know that Ag plus is a good oxidizing agent?
Has the positive or positive
Positive what?
reduction potential.
Yeah, positive E naught value, okay? That's exactly what Gracie said. If you look at Ag plus, hey, that's a good oxidizing agent because it's kind of up, farther up on the over-under. It's farther up there on the list, right? And so it wants to take in an electron. Now, if I gave you a choice, which one would be the better oxidizing agent? Ag plus or Na plus? Which one would be the better oxidizing agent? Peyton. Which one would be the better oxidizing agent?
The Ag plus,
Fantastic. Why?
because it has a higher E naught value.
It has a higher E naught value. So it's more willing to take in electrons. Sodium doesn't want to take in an electron and turn into elemental sodium, okay? Because it's not stable, right? This is why when you have elemental sodium, we have to store it in oil, okay? We can't let it be exposed to the air. We can't let it be exposed to water. Because if we do, it's going to turn back into a sodium ion. Okay, so when you look at question 47, so let me give you a hint. On 47, your first element in your list should be the potassium ion. Okay? So it's going to start with the potassium ion, and it's going to end up with IO3. So you're going to start at potassium, you're going to end up at IO3. Okay? On question 49, you should have 2 no's and 2 yeses. On 50, you should have 1 yes and 2 no's. When you get to question 51, make sure that you have given a justification. So let's talk about 51A and what it can't be. So you have to look at what you have available. It says, which one is the strongest oxidizing agent? Okay? Strongest oxidizing agent. So you're trying to find the one that's most willing to lose an electron or the one most willing to gain an electron?
Gain.
Most willing to gain an electron, right? So let's just look at this list, right? So let's talk about Cl minus. Would Cl minus be a good oxidizing agent? Aspen, you're in the back and you shake your head emphatically no. What?
Does not want to make Cl2 minus.
Yeah. Cl is not going to take in an electron and become Cl2 minus. Okay? So as an oxidizing agent, Cl minus is not even within the realm of possibilities. Okay? Now, what if it was chlorine gas? Would chlorine gas make a good oxidizing agent?
Yeah.
All day long. How would you know, Evan?
Because Cl2, if you give it 2 electrons, it has a high E0 value.
Yeah. So, and this is why you have to pay attention to, are you talking about the chloride ion or are you talking about chlorine gas? Okay? There's a huge difference between the two of them. You say, hey, Burkamp, I want to double chemistry dog dare you to consume chlorine. It's like, okay, that's the bet. But what question am I logically going to ask you?
How much?
Yeah. Well, what form is it? Am I going to take in a chlorine ion? Okay, I'll put some salt on my food. Not a big deal, right? Chlorine gas? Not so much. Okay? Exact same number of protons, but the difference is that one lone electron out there in that valence energy level. So you say, hey, Burkamp, chemistry, double dog dare you. Chlorine. Chlorine ion, all day long. Chlorine gas, I'm okay. I think I'll pass. Okay? And that's the difference. So, if you look at this list, again, think this through. If you look at that list, why could you safely eliminate Ag, zinc, and lead from any potential answer for a good oxidizing agent?
Because they're solids.
They
don't want electrons.
Not so much.
They're getting oxidized.
Well, if they got reduced, okay, right? If they got reduced, what would the charge on all of those be?
A -1.
Negative. You'd have Ag minus, you'd have zinc minus, you'd have lead minus. You ever see any of those metals with negative charges? No. Because Mother Nature is a lazy prima donna, and Mother Nature goes, cool, I think not. I'll give it a hard no. Because it's not stable. What do those metals want to do? At best, they either want to be stable, or what do they want to do?
Give some.
Lose electrons, okay? They want to end up with positive charges. They don't want to end up with negative charges. So if you were to look on the periodic table, okay? If you were to look on the periodic table, not on the reduction chart, on the periodic table, okay? On the periodic table. Where would you find the best reducing agent? Top left, top right, bottom right. Where would you find the best reducing agent? Top left, top right, bottom right.
Bottom left.
Top right.
Top right.
Bottom right. Maybe bottom left.
Then it wants to lose electrons.
Okay.
On the periodic table?
On the periodic table.
Bottom left.
On the periodic table, not on the chart. On the periodic table.
Which agent?
I stand strong.
You say it strongly bottom left. Why?
Because fluorine's in the top right, and that's at the top of this one. So
Okay, I have a better reason.
Let's go with Evans.
So if it's a reducing agent, that means it really wants to oxidize. And if it wants to oxidize, it really wants to lose electrons. And at the bottom ones, the electrons are further away from the center of the nucleus, so they have less attraction to the center of the nucleus. And on the left side, you have just one lone electron sitting out there. So it's very easy to steal.
Fantastic. That is a beautiful answer. It makes an old chemistry teacher's heart just go. Thum, 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 thum. Okay? So Evan just gave a wonderful answer. Okay? If you're looking for a reducing agent, what are you trying to find?
Something that wants to be oxidized.
Something that wants to be oxidized, something that wants to lose electrons, okay? And the ability to lose an electron is reflective of how strongly that electron is held. And the further you go from the center of the nucleus out of the edge of that electron cloud, the weaker the attractive force is. So if you go, even if you compare lithium, sodium, potassium, okay, as you go down, potassium is really, really willing to give up that electron because of the fact that it's way out there in the nether regions, far from the nucleus. It's just like, hey, I could care less about that electron. Far away from it, it's not very strongly held. Go away, be free. Okay. So in contrast to that, where would you find the best oxidizing agent? Top left, top right, bottom right on the periodic table.
Top
Right.
Top right. Why? Because it's the opposite of what Evan just said. Fluorine is trying to fill which energy level? If you look on the periodic table, which energy level is fluorine trying to fill? Second one, right? So go down, second row down, right? Fill in the second energy level. So that's closer to the nucleus. Chlorine is trying to fill the third energy level. So since fluorine is trying to fill the second energy level, that means that it's really, really willing to take in that electron because it's so close to the nucleus. Now, this is also, as an added bonus of this explanation, this is why hydrofluoric acid is the only weak acid of the halogens. Because that hydronium ion is going to be held closest to the nucleus, so this is also why hydrofluoric acid is the only weak acid. Okay? Cool with that? Good? Got it? Okay. So, back to our story. So on 51A, I'll just give you this hint. It should be a positively charged cation. Okay? On 52B, that's going to be an element. Okay? On 51C, you should have 2 answers. Okay? So you want which species can be oxidized by the sulfate in an acidic environment. That's important because you got the H+. So there's a couple of ways you can figure out your answer to C. You can play the over-under game. Okay? That's an option. And that chart that I gave you that has all of the anions on it, sulfates. You can play the over-under game. You can also calculate the E0 values. And if the E0 value is positive, the reaction will take place. If it's a negative, it won't. And 51D should also have 2 answers. So 51A is an ion, 51B is an element, 52C is 2 elements, 52D are 2 ions. Okay? Anything else? Going once? Make sure on 35 and 36 that I can clearly see the E0 values and if it's spontaneous or not spontaneous and the overall balance equation. Okay, so make sure that I can clearly see those 3 values. Anything else? Going once, going twice, something. Okay, get that handed in. Okay, so one of the big defining moments that occurred and it turns out in all of science is this idea of concept of called Gibbs free energy. So Josiah Gibbs did his work in the late 1800s, early 1900s. So to give you some perspective on how important this is, Albert Einstein, okay, pretty sharp guy himself, said of him, he's the greatest mind in American history. So, you know, if you have Einstein saying that about you, hey, that'll look good on a resume, you know. Hey, who wrote your letter of recommendation, Einstein? Oh, cool. Okay, here you go. Here's your scholarship. Thank you very much. So, when we get into this concept of Gibbs free energy, and when you look on your equation sheet, eventually, you'll see that there's like 3 different ways that you can calculate this idea of Gibbs free energy. So, when we talk about Gibbs free energy, and we're going to first talk about it in terms of cells. So the reason that is called free energy is that you don't have to do anything to generate it. So let's say, in a very simple idea, let's say that you have a copper strip and you have a zinc strip, okay? And it's going to have a certain amount of voltage. Here's your salt bridge. And that copper is going to get reduced, so the electrons are going to flow in this direction. So anytime you have electrons that are moving, otherwise known as a circuit, those electrons have the capacity to do work, okay? So with the reason that they call it Gibbs free energy is that you don't have to do anything to generate the electricity. You don't have to do anything to generate the current, okay? All you have to do is drop a piece of zinc in a solution of zinc nitrate, put a piece of copper in a solution of copper nitrate, hook it up, boom, that electricity is going to flow. Now, it isn't like, oh, let's run the school by building a single zinc copper cell, okay? Not quite that much. But it's important in terms of the concept. So it's free in the sense that we don't have to do anything to make that electricity move. And when that electricity is moving, we can use it to do work, okay? Now, for those of you that haven't had physics yet, we're going to talk about work, okay? From a physics perspective, the simplest way to talk about work is that it's you exert a force through a distance. So if I take this remote control and I push it across my hand, I just did work because I'm exerting a force through a distance. Now, if I just hold the remote, I'm exerting a force, but I'm not doing work because it's not moving through a distance. So this idea of Gibbs free energy has two parts to it. The energy perspective, okay, which you can use to light up a light or something like that. But you can also take that energy and do work. You could make it turn a little motor and you could make it lift something, okay? So energy and work are intertwined. And because of that, whether you're talking about work or you're talking about energy, all of this is going to be measured in units of joules, okay? So if you look at a concept that unifies all branches of science, whether it's biology, chemistry, physics, geology, astronomy, whatever, okay? Energy is the unifying theme. You want to have energy. Oh, okay. ATP, ADP, you know, what's happening at the cellular level. Okay, hey, we want to have electricity. All right, we have to make electrons move so that I can make toast. Which
It's open.
no, don't tell anybody. Shh. It's not supposed to be.
Could I borrow Jenna for a yearbook interview?
Yes. Good luck. Okay. Okay. So this is this great unifying theme, and it unites all branches of science. So a couple of things about how you can calculate Gibbs free energy. So the one that we're going to use today is delta G equals negative N F E. Okay? So let me explain what the N is. You all have seen N before when we did the Nernst equation. What does the N represent?
Number of electrons.
Number of electrons. So this is going to be the number of electrons. Now, technically, this is going to be moles of electrons. Okay? And that has to come, listen to me, from the balanced redox reactions. Okay, so this is going to be that number of electrons lost, number of electrons gained. Okay? It has to be the balanced half reactions. All right. F is known as Faraday's constant. Named after Michael Faraday, English chap, kind of a cool thing on him. He actually grew up poor, was an apprentice to a bookbinder, started hanging out with the science nerds in downtown London. Actually, they developed what's called like Faraday's cage. There's a whole bunch of things that Faraday developed, even though he wasn't formally trained as a scientist. He did a lot of work with electricity. And actually, they think that was one of the things that allowed him to think outside the box in terms of electricity, because he hadn't been trained as in the actual old school thought process. So he could bring a new perspective into it, because he wasn't like, he didn't have the blinders on that says, oh, this is how science goes. So he could look at things from a different perspective. So Faraday's constant is the amount of charge on 1 mole of electrons. And that has a value of 96,500, and this will make sense later, joules per mole. Okay? So where you get this number is if you take a mole, which is 6.02 times 10 to the 23rd, okay? Electrons, okay? So that's how many particles are in 1 mole, 6.022 times 10 to the 23rd. And each electron has a charge of 1.60 times 10 to the negative 19th coulombs per electron. So if you multiply these two numbers together, so here's the number of electrons in 1 mole. This is the amount of charge on a single electron or proton. And no, I'm never going to expect you to know that number. Okay, it's just a number. Okay, and Faraday's constant is on your sheet. You don't have to memorize that. So when you multiply these two numbers together, that's how you get that 96,500. So that's the total amount of charge there is on 1 mole of electrons. So that's why when you look at this in terms of units, so that Faraday's constant this is where you get the per mole, because then that's going to cancel out the number of moles that are on that end. So N is going to be a positive number. Okay, that's just the number of electrons in the balanced equation. Faraday's constant, positive number, is the charge on 1 mole of an electron. Okay, 96,500. So the only variable that you can have in this is your E value. Okay, that's the only one that can be positive or negative. So one of the things you'll see, and this is on those lecture notes that I gave you, is that when you look at Gibbs free energy, and this is going to be true no matter how you calculate it, Gibbs free energy has one of 3 options. Gibbs free energy can be a negative value, delta G can equal 0, delta G can equal a positive number. Those are the 3 options for delta G. They each have very, very something. They tell you a vast amount of information depending upon the sign. So if you have a negative delta G, no matter how you calculate it, doesn't make any difference. That means that the reaction is going to be spontaneous. Okay? So all you have to do is get that reaction started. Okay? So now, this is where this matches up in terms of this equation. So if you look at delta G equaling negative NF times E naught. Well, N is always going to be a positive number. F is always going to be a positive number. So here's what you want to look at. If you have a positive E naught value, okay, leave Gibbs free energy discussion out of this. If you have a positive E naught value, does that mean the reaction is spontaneous or not spontaneous? Spontaneous. So if I have an E naught value that's positive, that means I'm going to multiply that by negative, and then I'm going to end up with a negative G. That's why that negative sign is lurking out there in front of that negative NF E naught. So that negative is going to match up with a positive E naught and make Gibbs free energy a negative value, okay? So that's why we have a random negative sign out in front of that equation. Now, delta G can equal 0. So what that means, that just means the system is in equilibrium, okay? So, just means it's in equilibrium. That means the forward reaction isn't favored, the reverse reaction isn't favored. It's just going to sit there, okay? Maybe there might not be a reaction. Maybe we'll get into reaction rates later. Tough to say. And then maybe the reaction is happening, but there's just no net change, okay? That's a possibility. Now, your third option is that you have a positive delta G naught, which oddly enough, that's going to tell you that it is non-spontaneous. Okay? So if it's non-spontaneous in the forward direction, that just means it's spontaneous if you reverse the reaction. So here's the classic example. It's supposed to get, like, it's weird, tomorrow's high is supposed to be like 72, and Thursday's high is supposed to be like 36. Welcome to Kansas. Yeah. Guys, you know. And so Thursday night, you're at home, it's like, wow, it's cold, I'm going to start a fire. Okay. So, I'm just saying. Stay with the story, okay? And so you start this fire, right? You throw a match in there. You do have to throw in, we'll get into activation energy later. And you start the fire, you light the match, boom, wood starts to burn, okay? So the short version of this is that it's a combustion reaction. The carbon is reacting with the oxygen, and there's some hydrocarbons thrown in there with the wood. And you're going to get carbon dioxide and water vapor out of it, okay? It's a combustion reaction. And it's exothermic, which means you're going to be giving off heat. That's the whole point of lighting the fire, is because you're going to release heat. So once you get the reaction started, it's spontaneous, which means the overall delta G for this reaction is going to be a negative value. So here's the classic example. So in this direction, it is spontaneous. Now, if you try to reverse it, let's say, I want to try and make a twig. Cool. Okay? So I'm going to take a container, such as this, and I'm going to ingest some carbon dioxide and a little bit of water. Okay? I'm going to put it in there, and then I'm just going to start shaking it around. Okay? And then I'm going to shake that for like 10 minutes. I'm going to open it up, and I'm going to see if I've made a twig. Okay? Which would be cool. Don't get me wrong. It's like, here, watch this, kids. Open it up. I made a twig. Okay? No, it's not going to happen. Okay? So this is spontaneous in the forward direction, but if I try and reverse it and take carbon dioxide and water and try and make a branch out of it, that's not going to happen. Okay? So this is like the classic example. Now, I could do that, but I'd have to put a lot of energy into it to reassemble the carbon dioxide and the water into a twig. Okay? I could do it, but it'd be tough, right? Because I'd have to put so much energy into making that happen. So that's like the classic example of what's going to take place, where it's spontaneous in the forward direction, but it's not spontaneous in the reverse direction. Okay. Now, the other, and we'll go through more about this. So, for example, you can also calculate delta G. You can delta H minus T delta S. And we'll talk more about this equation later when we get into thermodynamics. But delta H is what we call enthalpy. It's how much energy is released or gained in a reaction. Delta S is what we call entropy, which is a measure of disorder in the system. And T is going to be your temperature. So, but it's the same idea. So if delta G here coming out of this reaction, if that's negative, the reaction is spontaneous. If delta G is a positive number, it's not spontaneous. If delta G equals 0, that just means the system is in equilibrium. Okay? So no matter how you calculate delta G, it always works off the same parameters. If it's negative, it's spontaneous. If it's positive, it's not spontaneous. If it equals 0, that just means the system's at equilibrium. Okay? That's it. All right. So how this plays out. let's say that we're gonna do this reaction. Okay. So basically what would happen is this. We're going to take elemental silver, we're going to let it be exposed to oxygen in the air. H plus, which means how are we going to make, how are we going to get a bunch of hydronium ions?
Acidic.
Yeah, it's going to be in an acidic environment, okay? So basically, I'm going to dump in a bunch of, I would take a piece of silver, I'm going to put it in an acidic environment, I'm going to let it exposed to the air, so it can, that's where it can get its oxygen from. I don't want to get silver ions and water. Now, what could I physically watch? What's the only thing that I would physically see happening if this reaction was taking place?
The silver would dissolve.
The silver would dissolve. That's the only way I would know this reaction is going to take place. So if this reaction took place, I wouldn't see a color change, okay? I would see the silver dissolve. But if I had a pH probe, what could I see changing if I had a pH probe?
It would become more basic,
Why?
because you'd be getting rid of hydronium ions.
Yeah, I'm gonna be consuming a whole bunch of hydronium ions, okay? I wouldn't be making bubbles, I'm not making oxygen gas, I'm not making nitrogen gas, so I would see two things happening. If this reaction took place, I would see the silver dissolve, because it's going from elemental silver into the silver ions, and if I had a pH probe, I would see the pH go up, because I would be decreasing the concentration of my hydronium ions. So there's two ways that I could determine if this reaction is going to take place. Now, if I want to calculate the Gibbs free energy for this reaction, the first thing I got to figure out is what's reduced and what's oxidized. Dear Lord, this is why I don't, anyway, go ahead.
Can I borrow Jenna again?
Is this the last time?
Yeah. take a
Promise?
picture. Yes.
Okay, then you can. You want me to say no? It's like, no, you can't ever, no. Okay. So here's the story. So this is a little bit tricky, mainly because of the fact that if you look at this reaction of oxygen and hydronium, and you're producing water, so on that reduction chart that I gave you, okay, the big one that has all of the anions and all of the polyatomic ions on it, this reduction is a separate thing. We're going to be dealing with water later on. So with this one, you have 4H plus O2 plus 4 electrons yielding 2H2O. And if you look on that, that has an E naught value of 1.23 volts. Okay? So don't look, because of the fact that you're producing water, this isn't oxygen, this isn't hydronium ions, this is the whole reduction potential to take hydronium, have it react with oxygen, gain 4 electrons, and you're going to produce water. And again, everything should balance. So I've got, this is why you have to have these 4 electrons, because I've got 4 negative charges here, 4 positive charges there. Oh, that adds up to equal to 0. Water molecules are neutral over here. I got 4 hydrogens, 2 oxygens, 2 oxygens. Boom, there we go. Okay, so this is a spontaneous reaction. This wants to happen, and I know that because I have a positive E naught value. Now, thank God that happens, because if this reverse reaction was favored, if it was more favored to produce hydronium ions and oxygen gas, we wouldn't have much water on this earth, because of the fact that if that reverse reaction was favored, water would tend to spontaneously split into oxygen and hydronium ions. So you'd have really, if you had any solutions at all, it would be really acidic because you'd be generating hydronium ions and the percent of those oxygen in our atmosphere would go way up. So it's a good thing that this reaction goes in the direction that it does. Now, the other one, so there's your reduction. So in terms of your oxidation, Ag is going to turn into Ag plus. Now, here's the deal. So when you look at this one, oxygen here is actually, or excuse me, the silver is actually getting oxidized. Okay, you all are used to, most of the examples that we've given, the silver has actually been reduced. The silver ion takes an electron and turns into elemental silver. Okay, that's what I showed you all yesterday, okay, when I had the, wherever that beaker went, the beaker
it's
that
right
had, yeah, right there, okay? So so that's that beaker we started with yesterday. Notice that that solution has turned a really dark bluish color because of the fact that we've generated so many copper ions and the silver got reduced. So in this situation, silver is actually getting oxidized. So if you look at that, that becomes negative 0.80 volts. You add these together. So right away, I have a positive E naught value for the entire reaction, which means, cool, this is going to be spontaneous, okay? So the first thing that you have to do is figuring out the E naught value. The next thing you need to do is figuring out what's the value of N. Well, if I've got 4 electrons up there, I'll only have 1 electron here, I got to multiply all of that by 4. So right away when I do that, now I know my N value. Now I know my N value is going to be 4. So I know my N value. I know Faraday's constant, 96,500. Now I know my E naught value of 0.43 volts. And remember, volts are joules per coulomb. So if we do this, we're going to take negative 4 times 96,500 joules per volt mole, which is an odd combination, but it works. And then we get 0.43 volts. So the volts cancel out. We've got 4 moles. The moles cancel out. I'm left with joules. You multiply all this together, and you get, negative 1.7 times 10 to the 5th joules per mole. Now, if you don't like big exponents, because typically these are pretty big numbers, okay? So you can either work in joules, or if you don't like this, a lot of times you'll see this expressed in kilojoules. So if you want to take that, and remember there's 1,000 joules in a kilojoule, so if you want to take negative 1.7 times 10 to the 5th joules and go, oh, there's 1,000 joules in 1 kilojoule, and you get negative 170 kilojoules per mole. Okay? I don't care which one you do, but you have to tell me, are we working in joules or are we working in kilojoules? Okay? Because if you just put negative 1.7 times 10 to the 5th, I have no idea what that means. It makes me no difference. My answer key has answers in joules, and it has it in kilojoules. Okay, it's a personal preference. I don't care. But you have to tell me which one, how you're going to play this out. Do you want this to end up in joules, or do you want it to work up in kilojoules? That's a decision that you have to make. Okay, I'm done. Because I got it uploaded anyway. So, let me explain what's going to happen on these reactions. So on 1A and 1B, I've given you the overall reactions, okay? They're not balanced by any way, shape, or form. So on 1A, for example, you've got chromium ions turning into dichromates, you've got fluorines turning into Cl minuses. So do not even think you're going to answer it on this sheet. Do not even think you're going to work this assignment on this sheet. Do not even think about it. Okay? Don't, I'm telling you, don't. Okay? So the first thing that you got to do is go through and figure out the half reactions. You got to figure out the redox half reaction, the oxidation half reactions. You've got to figure out the E naught values. Add those together. You have to have the overall N. Dear Lord. So help me God.
Is there any way I can interview you briefly for your book?
Absolutely not.
You can capture the anger.
If you need a picture, take it now.
Yeah, just be like, absolutely not.
Yeah, you should still know one day.
Talk to the camera.
We should all go to like the journalism department and knock on their. Excuse me, can we just interrupt you for just a second?
And then we have to leave, and then we have to come back 10 minutes later.
Okay. So I'll tell you right now, 1A is one of the more complicated ones because of the fact that you have dichromates, you have oxygens, and you got to have hydroniums. 1B is pretty simple because that's just Cu2 plus turning into magnesium. So on 2A, I've given you the E naught values, okay? So on 2A, you want to choose a set of conditions that produces a spontaneous reaction. So that means what you want to do on 2A and 2B, you have to figure out which one is going to get reduced and which one's going to get oxidized so that you end up with spontaneous reactions. The same thing is true of 3. Now, on 4, when I say calculate the maximum amount of work that can be obtained, maximum amount of work that can be obtained is the same thing as your Gibbs free energy. Okay? So Gibbs free energy and work mean the exact same thing. So again, on 4, you've got those reactions. You're going to have to look up the E naught values, figure out which one's going to go forward, which one's going to get reversed. Evan?
Would the number be negative for work as well?
Yes. Okay, when you get to number 6, okay, notice on all of those I have the words explain, okay, on the end of them. So give some type of justification. You might say, hey, this produces a positive E naught value. It's an over-under situation. This is above, this is under. So if you look on 6A, you got which is the strongest oxidizing agent, which is the strongest reducing agent. Again, think through what that's asking. You're trying to find, for example, on 6A, you're trying to figure out the strongest oxidizing agent. Oh, cool. You're trying to figure out the one that's going to be most likely to be reduced. You're trying to find the one that's most likely to take in electrons. Okay? And again, look at this. Do you think elemental iron and elemental tin are going to want to take in electrons to become negatively charged ions? No. So on 6A, you can eliminate the iron, the magnesium, and the tin. It's not even an option because they're not going to take in electrons. When you get to number 5, B, you've got to do some stoic on this one, okay? And if you remember back from your Chem 2 days, or if you don't, 1 mole of gas under standard temperature and pressure contains 22.4 liters, which is the same thing as this, okay? So standard temperature and pressure, 1 mole is this. Keep in mind that it's chlorine gas, so it's diatomic. Okay, all right, I'm done. You're on your own. Be free.